Scholars Panel again. As you know, my name is Moses Friday and today we'll be taking mathematics, Mth102, second semester 100 level. Alright, so one of the most difficult courses you guys are about to attend and to deal with so far is integration and differentiation in mathematics. Today we'll be looking at differentiation, and I believe that as you are looking at it, of course, you'll be differentiated. But then let's dive into this real quick and fast. What is differentiation? There's a technique in mathematics that permits you to find the derivative of a function. Right? The derivative of a function in the sense, let's use this example now. Should in case you have sugar cane or you plant sugar cane, all right? And at the time when it is about to be harvested, you harvest them, and of course you move them to a plant. Either you sell that raw or you move it to a plant that transforms your sugar cane into sugar for you. Now that conversion from sugar cane to sugar is what we call differentiation, right? And it works this way. There are a few signs and a few symbols you'll be seeing under this particular topic. Now, most of the time, of course, the symbol is written as dx. Now, what this means is we will be differentiating in respect to x. So, in case you have a function y equal to x to the power of 3 plus 2x, and we're told to do or to differentiate the function completely, we'll be dealing with dy over dx. And in dealing with this, there are a few rules of differentiation that you will have to know offhand. One of those rules is when you are told to find the ddx of x to the power of n, okay? The answer would be the exponential power is carrying n comes to the ground of x, and then you subtract 1 from the power itself, n minus 1. Now, this is the differentiation of x to the power of n. How about you have a of x to the power of n? How do you do this then? Now, let's look at this part. ddx of a of x to the power of n should give you, since there is a constant, or not actually a constant, since there is a coefficient of x sitting on the ground n, which is a, when the exponential n comes down to join the coefficient of x, it becomes an of x to the power of n minus 1. It's a basic differentiation rules. Now, the second one I would like us to look at is the ddx of the constant. Let's say a. The ddx of the constant a, alright? At the end of the day, we will end up having 0. The ddx of the constant is 0. Nothing more, nothing less than that. Now let's look at another rule. The ddx now what do we look at now? ddx of log x, okay, is equal to 1 over x. Okay? So look at the ddx of f of x, okay, plus g of x is the same thing as the ddx of f of x plus ddx of g. Sorry about that now. Of g of x. What it means is that differentiation preserves addition. At the same time, differentiation preserves addition, preserves subtraction, and of course, preserves multiplication. Now, the only part of differentiation that does not support or that does not preserve any of these operations is when it comes to division. Now, as we go further, we'll get to witness the different types of differentiations we can do, the different rules, and the different methods and techniques of differentiation, of course. Now, we have differentiation of direct differentiation, okay? We have differentiation from first principle, differentiation using product rule and differentiation using quotient rule. We also have what we call a function of a function, which is called chain rule. Then we have other parts of differentiation, especially higher derivatives. And higher derivatives are very, very interesting, but then we'll take this one step at a time. Now, should we have a case where we have a function differentiation on its own, there is what we call direct differentiation and what we call differentiation from first principle. Now, the formula f of x, not even just f of x now, in h tends to 0 of f of x plus h minus f of x all over h, where h is what we call increment in x. Increment in x. This formula controls the direction from differentiation from first principle. And let's look at an example. Alright? Now in direct differentiation we'll be dealing with direct differentiation and we'll be dealing with differentiation from first principle. So let's get started as there is not enough time. So the formula will be going up here in h tends to 0 of f of x plus h minus f of x over h. So let's look for example 1. Differentiate 3x squared. Okay? Now we could take for assumption that the function is named y. So y is equal to 3x squared. Now, if we are told to differentiate y, that means we'll be differentiating this y in respect to the variable it is carrying, x. So that the dy dx equal to. Now, from what we learned earlier on the rules of differentiation, we discussed that when it's carrying an exponential and there is formally a coefficient of x resting as the base, we multiply the constant, or not the constant now, we multiply the exponential, multiplied by the base. So that will be here in this case 2 multiplied by 3, giving you 6 into x. Then we subtract, of course, 1 from the power of x. So this goes to give us 6x to the power of 1, which returns back 6x. The surprising thing about differentiation is no matter the method you follow, at the end of the day, you will arrive at the very same answer. Now let's work this out. We'll be doing differentiation. As I said before, this is direct differentiation. I call it DD, capital D, capital D. And now we will be using differentiation from first principle. Now, like the formula is at the top, what will be happening is that at every single place, the function itself is 3x squared. But here, what does the function ask us to do? Whenever we see x, we add a plus to 8. So when we are writing this function for this part, it will be the function of x plus h should be equal to the function you have 3 in bracket. X has now become x plus h. X plus h all squared. Minus the function x itself, which is all of this, of course, which is 3x squared. Okay? So that means we'll have to include this in this part. F of x plus h minus f of x. Okay, now breaking that into our formula, we'll have in h tends to 0 of f of x plus h minus f of x all over h. That brings us to in h tends to 0 of this now 3. Now let's try to expand this. X plus h into x plus h minus 3x squared. So let's do this over h, of course. Let's not forget that. And being h tends to 0, x times x. That's 3 into x squared. X times plus h plus xh. H times x plus xh again. And then plus h times plus h plus h squared. Minus 3x squared all over h. I guess we're following. So leave h tends to 0 or 3 in brackets x squared plus xh plus xh gives you 2xh plus h squared minus 3x squared over h. So we go further to say h tends to 0. Or let's multiply the brackets. Open the bracket now. 3 multiplied by x squared gives you 3x squared. Plus 3 multiplied by 2, that is 6 into xh. Plus 3 multiplied by h squared, that's 3h squared. Minus 3x squared, of course, all over h. Now you'll observe with me that here, the positive 3x squared can cancel a negative minus 3x squared, leaving us with the h tends to 0 or 6xh plus 3h squared over h. Now, if you're going with me, you will observe that h is common to both sides of these terms. The term 6xh and the term 3h squared contain h. So we could factorize h out of the equation by having h in brackets 6x plus 3h over h. Automatically, the h here removes this h off. Now permit me to continue on this page. Okay? So this will give us finally the h, well, we are almost there, finally, the h of 6x plus 3h. The h tends to 0 basically, of 6x plus 3h. Now what the limit does, alright, is that wherever you find h, you have to insert 0. And so the moment you apply that h being equal to 0, instantly the whole of the h tends to 0 leaves the equation. So that means we'll be having 6x plus 3 into bracket 0, which will give us 6x plus 0, which will give us 6x. Now looking at what we have from the answer from direct differentiation and what we have from the answer from first principle, you can observe that there is no difference between the both. Now we'll be doing more complex examples on first principle, but this is an introduction to the two basic types of differentiations that we have, okay? The direct differentiation and the differentiation from first principle. Now let's go a little bit deeper and talk about gradients. Now what basically are gradients? All right. Okay, now let's proceed to gradients of functions. Now, the gradient of a function, in case I give you an example, let's say, find the gradient of the function 3x squared plus 5 at the point x equal to 3. Now, in this case, of course, I believe that many of us will want to use our knowledge of functions to basically solve this, but it doesn't work that way in this part of our work. The first thing you need to do here is to first find the derivative of the function. Mind you, what we did before, the y dx, is the same thing as f prime of x. What this means is that the symbol one you are seeing above the f symbol shows that we have taken the derivative of the function once. So when we increase the derivative of the function to 2 times, it automatically becomes the y squared, becomes d square y over dx squared. Now, should there be any situation where we have to find up to the 3rd derivative, we call that the cube y over dx cubed. I believe that this is self-explanatory. Now, returning back to our function, we have to first find the first derivative of the function itself. And the function given to us is f of x equal to 3x squared plus 5. Therefore, the f prime of x, using direct differentiation now, using direct differentiation, 3 times 2, that's a 6, 2 reduced by 1 power and becomes simple power x. Now since 5 is a constant, we said earlier that whenever you take the differentiation of a constant, it becomes 0. So in this case, f prime of x is equal to 6x. Now we have been told that the point x equal to 3 is the point where we should find the gradient from. So that means at f prime, we have to find the value of x being equal to 3. So since the f prime of x itself is 6x, the f prime of 3 now will be 6 in bracket 3. So the f prime of 3 will be equal to, of course, 18. Now 18 is the gradient of the line. So you can clearly say from here, the reason why we're using direct differentiation in this case is because it is a simple function. Now there are functions that we cannot use something as little as direct differentiation for. Not that it cannot be used, but then it's cumbersome. And then you will have to find a way to understand it. But most of the time, of course, you could end up using your direct differentiation and it will give you the same result as it always gives the same result as your differentiation from first principle. Now, this is an example of finding gradients. I believe that with this very small example and this very little example, we should be able to deal with something harder when we get to that point. Now, can we quickly fast forward to differentiation, using first principle. It is something deeper than we have done before. Now, with the material I have here with me, there is something that I'm going to wish to share. Differentiation from first principle. The question I have here is x plus 2 over 3x plus 5. X plus 2 over 3x plus 5. Now, I would like you all to note some particular things that have been said earlier at the start of this class, which is that we have some rules that guide differentiation. We have the product rule, we have the quotient rule, and we have the chain rule. Now each of these functions have their own way of appearance. So when the function appears as f of u v, we use the product rule. When that function appears as f of u over v, we apply the quotient rule. When the function appears as, now how do I do this now? U, or let's say u, let's say y is the power of u, then of course we can use the chain rule for this kind of functions. Now, the particular example we are going into right now is something we could use the product, or not even a product now, a quotient rule to solve, but then we can use the differentiation from first principle, of course, to deal with it. Now, example 3. Example 3 says that we should find the derivative of x plus 2 over over 3x plus 5. A minute to confirm that question. X plus 2 over 3x plus 5, that's correct. Now, in this case, of course, we know that the formula for the differentiation of first principle is lim h tends to 0 of f of x plus h minus f of x all over h. Applying that to every other functions here, the new function now, of course, don't forget this is completely a function. So the new function now will be x. Here is x, right? So we replace it with what? X plus h. So we have x plus h here, okay? Plus 2, of course, over here is another x. So we're going to change to x plus h, of course. 3 into x plus h plus 5. Minus, don't forget, minus. Now the function of x itself is this, 3x plus 2, sorry, over 3x plus 5. So we have x plus 2 over 3x plus 5. Do not forget that all of this is over h. Don't forget, of course, your lim h tends to 0. I believe that from previous work so far, you have been told, or rather, I might have to take that course where it introduces you to the essence of the lim function. Lim h tends to 0. What this means is the limit of h is tending towards 0. Right? We'll get to that in one of our subsequent classes. So for what we have here, expanding what we have here, I might choose to skip the lim h tends to 0 until I get to my final answer, of course, and I could choose to write through every single time. Alright? For now, this is what we're going to do. X plus h, of course, opening this now, plus 2, over 3, opening this now, 3x plus 3h plus 5, minus x plus 2 over 3x plus 5. Now, permit me to say that the whole division I have here is something as divided by h. Okay? Now, looking for the LCM of these two, of course, I'll end up having 3x plus 3h plus 5 into 3x plus 5. Alright? Now, the whole of 3x plus 3h plus 5 divides this. Here's your 1. 1 multiplied by x plus h plus 2 returns you back x plus, let's not make that mistake here. 3x plus 3h plus 5 cancels this out, okay, remaining 3x plus 5. So we are having 3x plus 5 into, of course, what's at the top? X plus h plus 2 minus 3x plus 5 divides 3x plus 5. Remaining 3x plus 3h plus 5. In all of these, 3x plus 3h plus 5. In bracket, of course, I would have at the top x plus 2. Alright, permit me to, of course, fix it out divided by 8 at the very end. Now, from here, we're going to have to expand these terms one after the other. 3x multiplied by x gives you 3x squared. 3x multiplied by h gives you 3xh. 3x multiplied by 2 gives you 6x. Now we're done with 3x. Can we move to 5 now? 5 multiplied by x, 5x. 5 multiplied by h, 5h. And 5 multiplied by 2, 10. Minus, we write that very down. Plus 10. I think it's getting messy now. Plus 10, yeah, this better. Minus, let's put that in bracket. 3x multiplied by x, that is 3x squared. 3x multiplied by 2, that is 6x. Okay, 3h multiplied by x, that is 3xh. And 3x, sorry, 1 to that, 1 to this to that, and then 3h multiplied by 2, of course, 6h, plus 5 multiplied by x, 5x, plus 5 multiplied by 2, 10. We close that off. Don't forget that everything is divided by h. Now I think the board is getting kind of messy, so let's clean some things up very fast. From this point now, if I open the brackets, we're writing this now, 3x squared plus 3xh plus 6x plus 5x gives me 11x plus 11x plus 5h plus 10, let me write this, 3xh. Minus, open the bracket up, not even open the bracket up now, let's finish up what is inside. Now, should there be anything that's inside of the bracket, of course. So now, we see there is nothing to add up. If I am not mistaken, really nothing to add up here. 2 times 3h times 3x, no, 3x times h, and here, I'm trying to confirm this point now. This times that gives you this times that gives you this times that gives you this. Then this and this, of course. So it is. So let's keep moving. So minus, there is nothing here that can actually affect themselves. Okay, I see a 6x and a 5x. So that will be a 3x squared plus 6x plus 5x, 11x, plus 3xh plus 6h plus 10 over h. Getting very long here. Don't worry, it's simpler than you think. So this will be 3x squared plus 3xh plus 11x plus 5h plus 10. Of course, negative sign affects everything in the brackets, and you end up having minus 3x squared minus 11x minus 3xh minus 6h minus 10. Everything minus. Alright? Okay? Over h. I'm getting closer. Stay with me. Alright? So 3x squared, of course, minus 3x squared, that's a 0 there. 11x minus 11x, that's a 0 there. 3xh minus 3xh. Oh my. It's looking very simple now. So we look at 5h plus 10. Of course, we have a plus 10 and a minus 10. Wow, that is just 2 terms. 5h and minus 6h. Now let's come up a bit now. We use 6h. So let's say that we are using 5h minus 6h now. 5h minus 6h, of course, which is what? Minus h. Okay? Over, what do we have under there now? Oh, wow. Nobody called me to tell me I forgot something? Okay, you couldn't have called me, of course, because you don't know what I'm taking this class. But then look at this part. Before we divide by 8, we're supposed to divide by the whole of this. For each of the parts here, before dividing by h. So let's make that correction very fast. Now, coming back here, this will be divided by 3x plus 3h plus 5 into 3x plus 5. So that means everything here, of course, will be divided by h again. Please let's make that correction. So let's come to this place and say divided by h. Alright, here also divided by h. Okay, now let's write this one under here. 3x squared plus 3h plus 5 into 3x plus 5. Okay, this h also 3x squared plus 3h plus 5 into 3x plus 5. Of course, divided by h. So here, let's not make that same mistake. So let's open what's under 3x plus 3h plus 5 into 3x plus 5 divided by h. Very good. I like how smart you are. You're doing your work very well on your end. So from here, minus h over the whole of this 3x plus 3h plus 5 into 3x plus 5 multiplied by, okay? Multiplied by the whole of this now. When you change this to divided by h and you change it to multiplication, it happens to be 1 over h. When it goes 1 over h cancels h out. At the end of the talk, we have minus 1 over the whole of 3x plus 3h plus 5 into 3x plus 5. Surprisingly, I can't go any further than this when it comes to simplification. At this point, this is where the limit h tends to 0 that we started with in the beginning comes to play. Because in the final answer, we are expecting something very simple, but in the final answer, we are seeing a 3h. So I need to eliminate every h I find in my final answer by applying a limit h tends to 0. That tells me that whenever I see any h, I should just tend it to 1 to 0. Okay, so if I see h, I limit it to 0. That will end up giving me 3x plus 3 in bracket 0 plus 5, okay, into 3x plus 5. Giving you minus 1 over 3x plus 0 plus 5 into 3x plus 5. Stay with me now. I believe that I'll see the answer from here. Minus 1 over 3x plus 5 into 3x plus 5. Now you can agree with me that this function, or sorry, this thing is the same thing. I believe you know what this sign means. The 3 lines means equivalent to, so that is whatever is here is equal to whatever is here. So that means it's the same thing as minus 1 over. I have a function 3x plus 5 and another function 3x plus 5. When I multiply two functions of the same type together, what does it give me? When you multiply x and x, it gives you x squared, correct? So imagine that the whole of this is x and the whole of this is x. What does that give you? X squared. So we end up writing 3x plus 5 all squared. Now this is what we call the first derivative of this function. Now this is the f prime that I've been told to find. Therefore, this is your f prime. F prime of the function is minus 1 over 3x plus 5 all squared. Like I said, we'll be going from simple to complex in this topic. And so far, we've learned the basis of differentiation. Alright? Now, there are a few more rules you need to know of when dealing with differentiation. Now, a few of them, of course, I believe you have this written down somewhere or have a note close to you that you're using. So I'm going to start from this end. We'll play this off. And then we're going to introduce some very few things. Some very few things now. Okay. How about we are given the dx of sine x, cos x, tan x, cosec x, or not even cosec now, sec x. Okay? However, I thought to do each of these ones. Now, these things are definite rules on that integral that you do not need to study too much for to find answers to. Now, the dx of sine x has been given as cos x. The dx of cos x is given as negative sine x. The dx of tan x is given as, don't help me now, that is sec squared x. Okay? And of course, the dx of sec x is given as sec x tan x. Now, there are other ones we could also put in play, like the ddx of inverse functions, 1 over the square root of 1 minus x squared, which is of course 1 over sin theta, up sin theta now. Okay, so 1 over sin theta, not even 1 over theta now. There's the ddx of arc sin theta, or arc sin x rather. Okay, gives you 1 over the square root of 1 minus x squared. Okay, and then I have ddx of cos arc cos theta, or arc cos x, gives you 1 over 1 minus x squared. Is it 1 minus x squared now, or 1 plus x squared? I believe it's 1 plus x squared. Or one of them is a 1 minus, of course. Then ddx of arc tan x will give us 1 over 1 minus x squared. Okay? So we have inverse functions this way. Of course, primary functions this way. Now we're going to be applying a few of them in our calculations. Alright, so that will give us a chance to explore more of our works. Let's see what we have here. Yes. So yes, we've basically learned on how to differentiate using direct differentiation of course and differentiation of course principle. Now let's see what other thing this handout will want us to learn. Okay. Alright, so this takes us to the rules of differentiation. Now the rules of differentiation, like I said before, we already know them on the board. Product rule, quotient rule, and chain rule. So let's go deep into all of these parts. For product rule, as we have on the board, product rule has to be the function of u multiplied by v, where u and v are independent functions. Okay? So take for instance, or not even independent functions, they are independent variables. Okay, multiplied together. So now, take for example, I believe this is example 4 now, if I'm not mistaken. Example 4, find the derivative of